This video supplements the introductory comments already provided with the objective of placing a bit more context to the videos on biosensors and optics. It is intended this short video as useful prelude to your more intensive study of biosensors and optics, maybe even a bit calming, like this 1865 painting by Asher Durand characterizing a peaceful summer afternoon. Let's go forward. This course module essentially helps us move beyond the prior focus on analytes. First, we'll make some general comments on our broader look at the analytes, specifically those measurants with higher molecular weight or those that are uncharged. We'll then briefly talk about biosignals and biorecognition elements. Subsequently, we'll then comment on how the basic measurement system is slightly changed to accommodate this new class of measurements. This then leads to recognizing we're going to address new transducer options as part of the sensor system. Finally, we highlight the need to understand enzyme kinetics and binding equilibria as part of the mediated signal pathways. In this part of the course, we explain the kinetics for enzyme detection and the use of binding equilibrium to detect antibodies. The M&M kinetics basically elucidate enzyme substrate interactions, while binding equilibria are pivotal in antibody detection assays. These principles underpin reliability in clinical diagnostics, research, and vaccine development, facilitating accurate antibody detection and enzyme quantification. In the prior module, we focused primarily on small charged molecules that were amenable to measurement with ion-selective electrodes, or smaller molecules where amperometric systems were effective. Indeed, we even recognized that for modules such as CO2, the measurement was indirect through the measurement of pH. We find that measurement of pH is powerful and the sometimes easy affair, and so we cast pH as the focus of the end-of-term project. In this diagram, we note that the current module continues examining strategies not amenable to the electrical sensor analysis covered in the beginning of the course, but now are seeking to measure large molecule analytes such as nucleic acid, bacteria, proteins, and metabolites. As has been mentioned earlier, this portion of the course tends to examine just a few items identified on the left-hand side of the figure above. At the risk of being slightly redundant, let's comment on the biosignals just one more time. I call this raising our gaze a bit to help achieve a broader view of our work. Biosensor, short for biological sensor, detects biological elements, enzymes, antibodies, called biorecognition elements in living beings that can be continually measured and monitored. The sensor is a device that recognizes biological elements such as enzymes, antibodies, antigens, peptides, things that are in direct contact with an electrochemical transduction element, allowing the sensitive and specific detection of analytes. It's a mediated pathway. Electrochemical sensors, including amperometric, voltammetric, potentiometric, organic electrochemical transistors, photoelectrochemical, and electrochemiluminescent sensors, can be integrated into wearable, portable, and implantable devices to help enable point-of-care diagnostics and health monitoring. These are devices such as chemical canaries, biochips, glucometers, and immunosensors. There's no question that point-of-care devices are extremely popular, as the sales of fitness watches will attest. This drives a lot of R&D behind product development. Of course, a central theme in biomedical engineering department slogan is engineering better health. I encourage you to download the 2023 review by Wu from Nature Reviews, as this is almost like the ideal book chapter for this course module. It's a fairly easy read, and as a review paper, it is quite complete and quite contemporary as well. We return to the biosensor measurement diagram to illustrate the change needed to measure our expanded set of analytes. Recalling that our focus is often on analyte measurands, the difference now is that the larger molecular weight and uncharged state of the measurand change the process. And while it might be easier said than done, the big change we need to make is in adding a biologic recognition element that can interact with the analyte being measured. Indeed, there are many materials that can be introduced, and for the purpose of this module, we will focus on those materials that catalyze enzymatic reactions or produce signals that can be picked up with optical sensors. So we've seen this diagram several times, but the idea is to put the biosensor measurement challenges in context. Another view of this is shown on the next page. When we reviewed this illustration before, the focus was on electrolytes and electrochemical transducers. Now, we see that to pick up, say, antibodies or enzymatic products, we'll be looking at different transducer mechanisms. This to say that our lectures on biosensing will need to discuss and include topics of enzymatic reactions and binding equilibria as a prelude to a greater understanding of the way in which this class of biosensors operates. Digging in just a bit more, our measurement systems for enzyme and antigens can be expanded to now include the electrochemical measurement systems outlined in earlier presentations, but also includes optical measurement. For this reason, we have two videos as part of this module, each providing specific detail on related transducer measurement schemes. It is probably a good idea to take each video slowly and separately, as there are many subtle technical details that need to be understood to fully comprehend the biosignal measurement process. Our portfolio of measurement techniques will now include optics. It's a separate video. Along the way, it will be necessary to discuss three concepts. First, we need to look at the very basic model from Michael S. Menten depicting the kinetics for enzyme detection. In principle, there are several models that can be used to describe this phenomenon, but the so-called M&M model captures the key idea behind the technique of characterizing the initial velocity of the reacting products. The equations that are derived are very interesting, and it's actually a great exercise in theory of approximation. Second, the chemistry of binding equilibrium discussed to detect antibodies will be presented. And lastly, optical sensor characteristics are presented in the final video of this module.